Todd Desiato will be presenting on the hypothesis related to the theoretical operation of the Graviflyer and the video test results that have been achieved so far. He's going to be discussing the theory, future testing, and warp drive tech's lab equipment upgrades as well. So go for it, sir.
All right. Make sure I share the screen with audio. There we go. All right, can you see my screen and hear me okay? I'll take that as a yes. Okay, so the last week, Charlie presented the Graviflyer hardware that he got from Alexey in Russia, and Charlie is hard at work trying to make it fly. We all want to see it fly. So a lot of people were asking about the theory and how does it work, and honestly, we don't know. But here are some hypotheses and some experiments that have been done to sort out what it doesn't do. Okay, so just as a reminder, these are some pictures of the Graviflyer. These are actually flying. This one didn't fly. It's not constructed with any high degree of precision or good structural integrity. It's a bunch of pieces salvaged from a junkyard and put together. The rotating magnet plate is unstable and wobbles. It can be seen in some of the videos. It can be touched while it's flying, while it's floating, and yet it's very stable. Most likely because it's like two gyroscopes, though it's counter-rotating gyroscopes, but still it's you can touch it, so the high voltage from the Tesla coil isn't doing much. And there were several versions. They didn't always work. The last one he introduced didn't work. But, you know, as a group, we're pretty much in agreement that there's no signs of foul play or tampering, and we, you know, think this thing is something real. So back in September, I presented my hypothesis, which was spin-stabilized magnetic levitation, essentially the levitron. You got a ring of magnets, and the top spins by precessing around the magnetic flux lines. And this rectifies the force and holds it stable, very stable. So I thought there was some connection there between the two. So this equation is what, this equation is what came out of it. And you've got the force on the left, and we're taking the gradient of the magnetic moment dotted with the magnetic flux density. This gives you a potential energy, and you're taking the gradient of the potential energy, which should give us a force. And that's the same thing as what gravity is. You've got G is the gradient in the gravitational potential. So you've got one gradient countering the other. So there was kind of hopeful that this might work. So I constructed this, what I call the Gravicooler. It was a Graviflyer in a box, or at least most of it. I have the spinning aluminum disc. It had a mu metal disc sandwiched on top of it. Sometimes it did, sometimes it didn't. In this picture, it had the mu metal, and this one it didn't. And it was a motor, DC motor, 12 volt, attached to a ABS plastic box with mounted tightly with a Delrin insulated rod, because I charge these discs up to relatively plus and minus 10,000 volts, 10,500. It was my limit. So in this box down here on the right, we have a disc with no magnets, and on this box over here, we have a disc with the magnets. And this is what it looked like when it was all sandwiched together with a center disc. I tested it, just the spinning magnets, to map out the magnetic flux. This is iron filings in little cases, and when it's spinning, it maps out a region here where the majority of the flux is pretty much standing upright. And you can see that here, the dark line is where the magnetic flux is perpendicular to the surface, so standing upright. And the light colored lines are where the magnetic flux is parallel to the test film. These are the images of the 6 magnets, and you can see exactly what I'm saying here. And I tested this with high voltage, without high voltage, spinning it in the same direction, spinning it in opposite directions. I tested it with and without the middle plate. I did everything except apply a Tesla coil and ultrasonic vibration. However, at some random frequencies, at some random frequencies, the discs, this thing that Mark made for me at Falcon Space, rings like a bell, really loud. I get up to around 4,000 RPM, and it starts, resonating all on its own. So these were the results, that I got. It's in this video. Magnets. The vibration changes, the weight changes. It's all due to vibration. I'll try to smooth it out a little bit. So this is all the weight gain, not weight loss. High vibration, more weight. Low, half of the less vibration, less weight tolerance. Here it got smooth. This is steady when the vibration is constant. Pretty much nothing. No change, nice and steady. Off the high voltage. Weight went up a little bit, half a gram. That's so the vibration. Did it a lot. And the high voltage is off, the weight back down. Nice and smooth, it goes to 0. Got a lot of vibration, it goes up a little bit. Not down, up. lot of experiments with this before I got to this. Scale is very sensitive to vibration. It was resonating with vibration, and weight loss just kept getting bigger and bigger and bigger. Wow, Eureka! No, the scale resonated with vibration as it kept getting bigger.
All right, that's why I said
And
it
the
doesn't
tempo
work.
rate sampling
Yeah,
on the
21 kilovolts and spinning the motors at about 36 watts total. Nothing. All right, like and subscribe, because now I'm going to build a real Graviflyer and let's see what happens. Have a great
Okay, so that pretty much summed it up, is that spinning magnets in a 21 kilovolt difference field didn't generate significant forces that were measurable. It generated a lot of vibration, basically because it's extremely difficult to hit the middle of a disc and spin heavy magnets. Okay. So what went wrong? Essentially, the equations are, correct. It's textbook physics. I didn't come up with anything new here. What is basically happening is that the magnetic moment for each particle depends on Planck's constant, which is 10 to the minus 34. And I don't have enough participation of all the particles spinning and precessing to get a large number. And so the Planck's constant dominates and it doesn't move. So its order of magnitude is too small. And that's why you can't even get a reading. So this kind of puts the quash to anybody thinking that spinning magnets around with a high voltage electric field all on its own without the use of air is generating any lift on the Graviflyer. That was the whole point of putting it in a box, is there's no airflow. It's not pushing air away. Everything's in the box. And like I said, the only thing I didn't apply was the Tesla coil, which is a high voltage, but extremely low power, and the ultrasound, which is actually extremely low power too in this case. So what makes it fly? We don't know. Kurt Zeller joined our group a couple months ago, and he has access to console. So at least some of the modules. So he did some simulations, and we discussed the setup here with the Graviflyer and how it's all set up. So he modeled like electrostatic, magnetostatic, magnetodynamic, and electromagnetic, and also ultrasonic. Now, the magnetodynamic and electromagnetic are not done. Essentially, those two parts need additional modules, as well as if we wanted to test dynamics within the air, we would need a fluid dynamics module that we don't have. So this was the electrostatic, and you can see it looks like a parallel plate capacitor. You got negative voltage is the blue, and I mean negative voltage is the red, positive voltage is the blue, and this is your scale of voltage into kilovolts. So we had plus and minus 10 kilovolts, and you can see the electric field in the middle is the strongest between the plates, right in here. And right through here, this is where you get the strongest electric field. And then this is the magnetostatics. You can see that even with 1 Tesla available at the surface of the magnet, what even barely penetrates the disc above it is, a fraction of that, less than 1/10 of that. So the magnets really don't have a lot of influence beyond their immediate realm, beyond their immediate volume. And the effect of the whole thing spinning with the charge, I couldn't even measure the magnetic field from the spinning charge. It didn't really show up on my magnetic film. It didn't really move the magnetic iron filings very much. So I can get more magnetic field out of a current carrying wire than I could out of spinning the 10 kilovolts on the disk. So relative to Earth's magnetic field is trivial. It exerts no force at all. So then we started looking at eigenmodes and vibrations. So I had a 9-inch disc available to me. So Kurt ran a model to find all the eigenmodes and one to find the axisymmetric eigenmodes. All the material is linearly elastic and isotropic, no constraints, basic. So here we have 6 lobes. Here we have 2. This is actually anti-symmetric. Here we have 7. Here we have 8. So 6, 7, 8 lobes. And you can see it kind of looks like a petal of a flower, a flower petal, or a sine wave projected along the edge of a plane. This is how these modes resonate, and these are all less than 1 kilohertz. Well, not that one, but there's also modes like this, and many modes, ridiculous number of modes. This is a really high mode. 14.8 kilohertz, because we were thinking ultrasonic, and you can see at ultrasonic frequencies it's all over the place, and the amplitude on this is very small. So at those frequencies it may not be doing much. It's more likely that if there's deformation of any of the discs, the 9-inch or the 15-inch big disc, that they would be in lower frequency modes than the ultrasound mode. But we don't know yet. So in order for this thing to support itself using air as the medium, it's about 1 kilogram, Charlie said. So that's 10 newtons of force is required for it to hover. So for a 15-inch diameter disc, this would require about 80 pascals of pressure, a difference in pressure above to below. So through the big disc, you'd have to have a difference of 80 pascals of pressure. And that's just basically the rocket equation. You've got the difference in pressure over the area of the nozzle. So in this case, the nozzle would be the resonance of the disc. But as Kurt points out, the steady state vibration should produce equal pressure rise and fall above and below the disc across the oscillation period. So what could create a steady state pressure imbalance? So is it the ground effect against the disc below it, or the disc above it? Is it a standing wave between them? Is it ultrasonic sound pressure levels? Here's a couple of ultrasonic resonators with some styrofoam floating in the pressure nodes. Could it be that between the 2 plates and the ultrasonic transducer, it's generating enough pressure nodes for that middle plate to sit on? According to the limits of that technology, it can lift things denser than aluminum. So it is possible. Could it be that the dynamics of the vibration are similar to a Woodward mega drive, that's Mach effect gravity assist drive, and that there are accommodations of first and second harmonic at work here that are actually exerting forces on the vacuum or on distant matter, as Jim would have it? Or is it some kind of hidden aerodynamic lift? That would mean moving a lot of air like a wing or a propeller. Let's take a look. So if we had discs such as, this 7-point disc or this 6-tier disc or this 8-tier disc, and it really had very strong deflection, then as it rotates, it's going to act like a wing. It's got an angle of attack as it hits the air, and that can generate lift. I have a video that is actually inconclusive. Excuse me one second. So I have a video where I tested this. I bent one of my discs and spun it, and my rickety scale did show some weight loss because of the lift. So it could be that when it vibrates and it gets resonating at an ultrasonic frequency, the rotors physically deform and give you an angle of attack on the air, which then generates lift. And that's actually a pretty high probability of that being the case. Number one, it definitely involves some resonance. And two, is it's the only thing that can push enough air to generate 10 newtons of thrust. So that's the next hypothesis in line. Another hypothesis is Helmholtz oscillation, sound from propulsion. And I got another video for you to watch.
Demonstration that goes along with this one. So I have two Helmholtz resonators, and they are, one is pointing that direction, this other one is pointing this direction, and both of them should have their corresponding jet in action, right? And if I mount my two Helmholtz resonators on a pivot, and there is the bearings right there allow for that kind of motion. Actually, let me start it this way. So I'm going to start it the opposite direction.
So there you could see sound pressure coming out of those nozzles in resonance can exert quite a bit of thrust, and this could be optimized. So here, to demonstrate, as the air comes out of the nozzle, it creates a vortex ring. And so here's another video to show you the power behind.
According to legend, a really good blast of air should be able to bring down a house of straw. Let's see how it goes with an explosively generated vortex ring. Here goes. This is the gas. It's the first time it's ever been fired, and with 150 litres of one of the world's most explosive gas mixes in there, I'm not even sure that this is really a safe place to stand. Seems about right. I'm going to need these, I reckon. Here we go. 3, 2, 1. Oh, yes! Call me hopeful, but there was definitely something there. But was it a vortex ring? Filmed at 1300 frames per second, there is no doubt. But the ring you can see is not a smoke ring. It's formed by the pressure drop within the vortex, condensing the water out of the damp air above the lake. A 200-mile-an-hour cloud. Ho, ho, ho. Bring on the sticks and bricks. Three, 2, 1. What? Yes! Fantastic! Well, it makes mincemeat of a house of sticks. Bring on the bricks. Even in fairy stories, they couldn't get a blast of air to knock down a house of bricks. We're heading into the world of the unknown a little bit, so we've got to experiment. We're going to try changing the elevation on it, changing the gas mix in there, see if we can get a perfect gas mix. So that's just the right amount of molecules of acetylene reacting with just the amount of molecules of oxygen in the air. So there's no passengers in there, it's got to be all explosion. Let's see how that goes. Three, two, one. Hey! Yes! That's incredible!
So you can see the force come behind vortex coming out, vortex rings coming out, and this causes turbulence. So what Kurt was saying about the pressure is the same in both directions. As soon as you do something to rectify that so that you've got a resonator closed at one end, so to speak, like a pipe closed at one end, or a pipe with a diaphragm at one end, then what comes out the other end forms vortex rings, and the vortex rings propagate away from the nozzle so that it propagates momentum away and generates thrust. So it's like an air breathing thruster. And so Alexey's invention here is using resonance, and you've got the positive plate above, you've got the negative plate below, and then he's got the Tesla coil feeding an AC voltage to the plate in the middle. That plate in the middle could be resonating and generating any of those waveforms to push air in such a way that it's shedding vortices. So they call it vortex shedding. So between the spinning and the ground effects and the resonance effects, it can generate lift through vortex shedding. And this was basically another hypothesis. So Kurt wrote down what it would take to do an ion lifter, and the calculations are here, but essentially it's a factor of 100 too small for 1 Newton. I mean, for 10 Newtons for 1 kilogram. So could having ions in the air around the Helmholtz oscillator, could the electromagnetic field be used to help accelerate and push the air so that you get more momentum and more thrust off of the vortex ring that you push out? Could you push it out harder if the vortex ring were charged and you're pulsing the electric field negative at that time, the electrons are spinning in that vortex ring, and you push the vortex ring away harder. So tuning the resonance between the vortex manipulation or creation and the electromagnetic field may amplify the effect. So adding ion thrust with a vortex generator with the Helmholtz oscillator could generate that 100 times difference. So in order to test these things, and thanks to some very generous donations and contributions to our group in our lab, I acquired a ultrasonic microphone that's flat frequency response up to 50 kilohertz. And I acquired some imaging equipment so that I can do Schlerin imaging. And Schlerin imaging at a high frame rate. And by that, I mean about 1,000 frames per second. So for frequencies below 1 kilohertz, that works fine. Mark is hoping we can get a very high, ultra high speed camera, but that's a couple of orders of magnitude difference in cost. So, but for right now, I have this set up, and I set up this color Schlaren. I built a little strobe light here so I can strobe it to see sound waves. I built the 2-color Schlaren film so I can get color Schlaren. I got a 6-inch mirror. Unfortunately, the mirror has quite a few defects and doesn't focus really well. It's got a few concentric rings in the middle, but I have another one that's actually an expensive precision mirror on order. It hasn't arrived yet. So one last video so you can see what Schlaren photography can do. Here we're going to view continuous sound waves. These are not standing waves. They're using a strobe light to the same, strobing at the same frequency as the sound wave, 21.56 kilohertz. And so it looks like the standing wave, it looks like the sound waves are standing still. Now they shifted the frequency of the strobe light, and now you can see the waves are propagating. But with this, I will be able to see the sound waves, the ultrasound being radiated by my Graviflyer. And I should be able to ascertain what's going on. It's looking, you're seeing is the change in the density of the air. And this got me thinking that the Alcubierre warp drive is almost identical and could probably be mimicked using air density. If you had like a snap ring, you know, a canning jar, it's got the oil can effect, they can go pop. What'll happen is when that oil can pops to one direction, the density on one side will get lower, the density on the other side will get higher, and you'll get a vortex ring around it that resembles the ring of negative energy density required for the Alcubierre warp drive. It's a very interesting analogy. I'm going to try it when I get this thing working well. Right now, I was unable to view the sound waves or the traveling waves with my strobe light. I think the problem is I don't have a clear enough focus with this mirror. It's not like those are crystal clear. Mine is not. And so I think this mirror is just not very good quality. It was $28 or something, cheap. But I do have a good one on the way, and then I'll do some more videos. So we have evidence that there's a flying machine that hypothetically, Charlie has the machine, but it can hypothetically may work by gradient forces mimicking gravitomagnetism. And I had that one crossed off the list, but we've checked that now, and that didn't work. That's basically my original equation, my original hypothesis, and that didn't work. So we have aerodynamic lift from an ultrasonic deformed rotor propeller. We have the Helmholtz resonator, an air-breathing ultrasonic resonator exerting pressure on the surrounding air to exert lift forces like per the rocket equation, or an air-breathing ultrasonic resonator exerting pressure on the surrounding ionized air plasma assisted by electromagnetic fields to accelerate the plasma at resonance. These are, in my opinion, the most likely theories of how this could fly and how Tic Tac might fly. So especially this last one, it may be related. Moving air at ultrasonic frequencies in an ionized plasma environment could be the technology that we're looking for. Okay, so what it's unlikely to be are forces due solely to electromagnetic radiation or gravitational wave radiation. Without medium assistance, that would require gigawatts of directed radiated power in order to balance out the weight of 1 kilogram Graviflyer against gravity. The Graviflyer would require a resonant Q factor of over 1 billion to achieve this. Therefore, it's unrealistic. It's just not likely to happen. So the other thing is the current ion propulsion engines without any sort of ultrasonic resonance, the current ion propulsion engines are pushing about 290 millinewtons of thrust, whereas the Graviflyer would require over 10 newtons of thrust to support its weight against gravity. So therefore, ion propulsion alone is unrealistic. So it's got to be coupled with something else. And in my opinion, because I get a lot of flack for this, anything that violates conservation of momentum and energy is unrealistic. But that's where I stand. These are the best theories we have to date. If anyone has any ideas, you can reach me at Todd Desiato at Warp Drive Tech, and I'd love to hear it. So I have a channel, Warp Drive Tech. We are finally over 500 subscribers. Thank you very much. If you'd like to support us and be one of our contributors, we have a PayPal and we have a Patreon, and I visit both frequently. So and do a lot of videos, and I'm getting more done every week. So I hope you'll tune in and enjoy. All right.
Todd, thank you, sir. Let me stop your screen share.
Okay.
Okay, and stop sharing. There we go. So everybody, what I want to do is give Todd a giant hand. In APEC tradition, Todd, thank you. Thank you for drilling down on the Graviflyer. Thank you. And I think it was really interesting to go into the vibration modes and the air effects as well. Okay, so let's do this. Let's